And yeah, I'm presenting Minefield today. And first a bit of motivation why we want to use Minefield. So the idea is to have undervolting. Undervolting is the principle or the technique to reduce the voltage of your CPU. Why is that useful or why is this important? Because with a reduced voltage, you also reduce the energy consumption of your CPU. So that's already the first part, energy saving. However, a more indirect part is then also that you can get a lot of more performance when you reduce the voltage. Why is that? Because of the modern CPUs, they have like thermal limits and thermal thresholds, and the less energy you use, the longer you can sustain such boost states or performance states, how they're often called, with higher frequencies. However, undervolting also has negative effects. So we have seen in the past that there are software-based attacks or hardware-based attacks for undervolting or against for your software in general, and mainly the blundervolt attack, the volt jockey attack, which used a privileged interface in order to perform an undervolt and attack SGX enclaves. However, we have also seen hardware-based attacks which basically intercept and build malicious undervolting package and send them directly over the bus to the voltage regulators on the chip. So what were the protections against that? For the software-based threat model, Intel removed this privileged interface altogether if you're using SGX. And we can see that this directly removes the first point of the slide, that we can no longer efficiently save energy or increase performance when even one single enclave is running on the whole system. For the hardware-based mitigations, Intel switched a bit their CPU design and moved these voltage regulators, which could be attacked with this wiretapping attack, into the package of the CPU, and they are therefore no longer accessible via the mainboard. So the question we ask in the paper is there not a better way that we can still have undervolting while having secure computation in SGX enclaves? And the high level idea of this paper is quite simple. We have an instruction stream and we build something in the between. In our case, it's a compiler extension that transforms this instruction stream to the following. We can see that we place trap instructions within the instruction stream, and these trap instructions are there to be checked by the program itself. The idea is now that if we undervolt a program, the trap instructions should catch that fault. And if the trap instructions detect a fault, we simply abort the computation. So how can we find such a trap instruction? The instruction set is quite huge. What would be the suitable instruction for these trap instructions? So to answer that question, we build a framework that uses the complete x86 ISA instruction set and executes each of these instructions in two different environments. First, we execute an instruction in a normal environment without undervolting. We record each of the intermediate results and then re-execute that instruction undervolted. And we simply check if we can observe a difference between the normal execution and the undervolted execution. If we detect such a difference, we simply report that this is a fault and we have found a faultable instruction and record all the environmental parameters. So how much did we undervolt, what was the frequency, which core was it, and so on. However, to the undervolting, we often have the case that the CPU just freezes and crashes. So to handle that, we also included a remote PDU that can restart the system remotely when it detects a fault. The results of this analysis revealed the following. So we can see here on the left, we see the graph where we have on the x-axis the frequency domain, on the y-axis the amount of undervolting offsets we apply. And we can see across the frequency axis that the IML instruction is the instruction that faults the earliest. So these are the faulting points when we saw the first point during undervolting. We tested overall more 1,200 instructions approximately across different CPUs, and we found overall 71 faultable instructions. And if we now use this IML instruction, which basically faults the earliest, we can already detect 92% of all other faults with the IML instruction. If we want to have more certainty on certain CPUs, they behave to be different, we also need additional instructions to protect against these remaining cases. So we have now found our trap instruction suitable for the mitigation. It's the IML instruction which was previously used in the text too. So we can now use the IML instruction to basically protect our programs. Let's consider these three instructions. We now use the compiler to basically, at first, insert a state in each basic block, we start the basic block by checking if these two registers, in our case R12 and R13, are still matching. They should always have the same value. Otherwise, we have detected a fault and securely abort the computation. We then insert these IMUL instructions in between, and we can also handle some cases where the IMUL instruction basically alters the state of the program, because the IMUL instruction also alters the flags register on x86. At the end of each basic block, we also make sure that the basic block contains an even number of multiplications, so that we always have the guarantee at the beginning of a basic block these two registers will match. What this compile extension enables us is that it's like a drop-in replacement, and we can recompile the complete SGX SDK and get fault suppression support. So we can detect faults, and we define a fault handler where we can abort the program safely. Since we've added now a lot of instructions, we have also to talk about the negative side of this mitigation, the runtime. Obviously, we add new instructions into an enclave execution, so we increase the execution time. However, remember back at the beginning, this benchmark only affects SGX enclaves and allows the remaining system to run undervolted and probably gain a lot from that undervolt. Also, as a factor here, we can also choose how many trap instructions we insert after a certain instruction. So if we just insert one instruction, we call it a placement density of 1. That's actually the x-axis you see. And if you insert 2 trap instructions after each normal instructions, that would be a placement density of 2. The more placement density they have, the higher your protection should be. So we can see that we have a linear runtime increase due to the added instructions. Also, the size is growing linearly, compile time. And we also wanted to take a look at software that had already software-based fault protections built in. So we took a look at the MBTLS library, and more specifically on the RSA encryption there. So they verify each encrypted text by decrypting it again and checking if the plain text match. So if we now remove this check and replace it with our Minefield implementation, we can see that there are even cases where Minefield outperforms this classic redundancy check. Yes. So, however, this is all the performance side. How does it look on the detection side? We also took a look at that. So we reused the Blundervolt POC in some parts of the Blundervolt POC, where we just tried to fault the result of multiplications. And this is basically the worst case, as we also use the IMUL instruction as trap instruction. So we benchmarking an instruction that is really likely to fault against another that's really likely to fault. And we can see on the top left, we can see the recall across the placement density, and can see that we have a good recall about 90%. However, the recall is declining after a certain placement density. And that's also reflected because the recall does not consider the case where we observed faults only in the trap instructions. Therefore, we also included the mitigation rate. Basically, if you see a fault in a trap instruction, you already know that the system is running near the critical limits, and you should no longer guarantee to execute the SGX enclave code on that system. So that already brings me to my conclusion. So we open sourced the complete LLVM extension. Also the SGX SDK, the modifications are in the GitHub repository, so check that out if you are interested. We also passed the artifact evaluation for the compiler extension and all the code. And also the undervolting framework to find interesting instructions is online and available. If you're more interested in more details, like the exact faulting points of each instructions, the analysis over the whole CPU range, and also defaulting mask, so how does the fault actually look like for different results, please take a look in the paper, and I'm happy to take any questions.